Hello, and welcome back. Today I would like to show an implementation of the Transvoxel algorithm as the next steps in this terrain engine. However, before I do that, there's a few corrections I need to make to a previous video I put out about camera visibility. There's two things that need to be mentioned here. The first is that the use of a fully visible cell is no longer, it's been removed. Cells are now either just visible or non-visible. The motivation of this is due to the fact that there may very well be occluders that are in a fully visible cell, and the detection trees would still need to be built, so there's really no savings that can be guaranteed here. So it's easier to just simplify everything to visible, non-visible, and create the visibility structures. The second thing to mention is that points for how they were generated to do the grid clip test, before they were being flattened to the plane of y equals 0. This only worked by happenstance though. If you began to rotate the camera from identity, it would no longer project properly. So instead of just using the 4 points, take each of the 8 Frustum vertex points and use those in the grid clip test, and that will give you the correct results. Now, with all that being said, let's get on to today's task at hand, which is the Transvoxel algorithm. In the previous video, I omitted some information about the marching cubes algorithm, as modified marching cubes really just builds on the fundamentals of the algorithm, and it allows for the real-time surface extraction with acceptable triangulation. Transvoxel, on the other hand, while it's still heavily based on marching cubes, does require a bit of explanation to get into the mindset of what it is and what the problem is that we're trying to solve. The paper does go into a brief history of the relevant techniques in Chapter 2, and a few of the motivations of the final algorithm can actually be seen from these previous works. The major problem that is ran into when triangulating voxel data at varying resolutions is that the extracted vertices don't line up, especially as slope becomes very steep. One solution to mitigate this problem is to generate two-dimensional polygons to fill the cracks. However, the shading results of this technique are less than optimal due to how the surface normals are generated. A second solution was to shift the vertices of the higher resolution cell so that the endpoints are collinear with the endpoints of the lower resolution cell. However, another issue arises here with very harsh seams along the stitch, as well as surface morphing in the higher resolution cell. These solutions also fail to handle situations in which a low resolution cell is trivial and a high resolution cell is non-trivial. Both of these techniques have their respective inspirations present in the Transvoxel algorithm. However, the key is a separate set of triangulation tables that are used. The actual proof on how these tables work delves very deep into group theory, and that is far beyond my ability to comprehend what's actually happening, but I can provide some insight into how to try and visualize what's happening. The groups which are relevant to the triangulations belong to what is known as D8, or the octic group. The thing to know about D8 is that it's a dihedral group, and dihedral groups contain the symmetries, rotations, and reflections of the elements of their group. This should ring some bells if you're familiar with the details of just how marching cubes works in general. Now, how specifically this was used to generate the tables, I have no idea, but the important part is that the resulting triangles are two-dimensional since the samples are taken along a flat 2D plane where the normal of this plane is that of the transitioning face. Here we can see one of the previous techniques of generating triangles to fill in the gaps of the transitions between the two resolutions. However, these samples give much better shading results and are guaranteed to be the right orientations to join high and low resolution vertices. The next thing to know about Transvoxel is the definition of what a transition cell actually is. These are special cells similar to the marching cube cells, and these fill in a gap of some predefined width between the high and low resolution meshes. It should also be noted that these are placed between the high and low resolution mesh on the low resolution mesh side. Later you will see how to shift the vertices, but that may have to be in a second part. But the thing to know about this is that it avoids the problem of surface morphing the high resolution surface, and the low resolution surface is able to match up again with the high resolution surface. The anatomy of a transition cell is also changed so that it's one where there's a high resolution face of 9 samples and a low resolution face of 4 samples. The 4 samples on the low resolution face match up with the 9 samples on the high resolution face, and that can actually be seen right here. Alrighty, so the first thing I would like to mention that this implementation does not account for transitions along the up axis. And I say up just because Y and Z are not necessarily interchangeable in this case, but depending on what space you're working in, X, Y, and Z or X, Z, and Y might be your axis ordering. The motivation for moving the up transition actually comes from an update to the algorithm that Eric made. I believe his implementation still uses octrees, and in doing so, it's still going to have up transitions for each level of detail, but each level of detail now spans the same physical size in the world. And this provides quite a few advantages, most notably a reduction in draw calls of the higher resolution meshes. Back in 2010, when he was first creating the algorithm, triangle count was your killer. So having the octrees of high resolution fill the space of lower resolution octrees allowed for very fine-grained LOD selection, but fast forward to 2022 and GPUs can handle vastly larger amounts of triangles, and now the name of the game is reducing the number of draw calls. So by creating each mesh to be the same physical size, you'll only be sending a handful of very high resolution meshes to be drawn, and once you shift to just the first level of detail, your triangle count drops by roughly half and continues in the same fashion for each successive level of detail. This will allow for a much longer viewing distance without sacrificing too much performance. The second thing which this new technique means is that blocks themselves at any resolution are massive. Now, I'm not saying that there will never arise a situation in which you might want to handle endless verticality, but in the situations which I foresee myself using the framework, I don't really see a need to go past the height limit that's already allowed by this technique. So in that case, this implementation may not work for you fully, but I do believe that the transition extraction, which is the hard part, and handling the primary, secondary, and extremal vertices, which is the even harder part, will still work, or at least be able to shed some light and clarity onto the problem for you. However, I am dropping the up dimension for extracting multiple blocks for 2 reasons. The previously mentioned one being I believe there's already enough room to work with, and the other reason is that Manifest works on a grid system. By making each grid cell the size of a block, each block will fit perfectly into one grid cell, allowing for very nice integration with the visibility and rendering systems, as well as providing some nice indexing techniques. One thing I do want to mention is that, if you're not aware, grids can be very dangerous if not handled properly, and they can grow uncontrollably. Since a grid traditionally requires each cell to be available for index reads and writes, the entire memory for the relevant cell data is pre-allocated. It's just something to keep in mind. However, by allowing the grid cells to be the same size as terrain chunks, this is a nice start to reducing the overall number of grid cells needed at any one point in time, and then you can start to look at streaming for loading and unloading data as it's needed or not needed. Now I would like to give an overview of the Transvoxel implementation as per the paper, and then I will dive into the code and show the generalized XY/XZ transvoxel implementation. As previously stated, most of the algorithm shares similarities with the modified marching cubes algorithm, but the biggest difference is that these transition meshes are two-dimensional in nature, as the entire mesh is extracted along a single constant sample in some axis. The paper specifically describes the process for positive Z block phase, with the XY axes being extracted on, but this can really be generalized down to any two axes, AB, who span the plane with some surface normal, N. It's this plane that we extract on. For example, X and Y can be remapped to A and B respectively, and Z can be set to N. This generalization can then be used to extract any of the 6 faces as needed by reordering A, B, and N for the face being extracted on. Similarly to modified marching cubes, a history buffer is also used when extracting a face to allow vertex reuse. Fortunately, unlike modified marching cubes, we do not need to make a distinction between edge and corner vertices, which greatly simplifies the task. Once the history buffer is set up, we can begin the extraction, and to start, we select the current location in the history buffer we wish to record to, clear out the values for later, and load the transition cell case index. Loading the case index is relatively straightforward, but there are a few differences from modified marching cubes, or just marching cubes in general. The first difference is that where the sample locations are, the sample locations still follow the same row then column sampling rules. However, all sampling is done only on the high resolution face of the block. The second difference is that there are 9 overall samples as previously mentioned. However, the 4 corners of the high resolution face are duplicated over to the low resolution face. This requires half and full steps to be taken when loading the cell. One last difference is that ordering in which bit shifting may be done is not incremental, whereas with marching cubes, each corner 0 to 7 represented by how far that bit should be shifted, and the code is how far is that bit shift. The same is not said here. As you can see, we have an ordering of 1, 2, 4, 80, 108, 40, 20, and 10. This gives us a bit shift order of 0, 1, and 2, 7, 8, and 3, 6, 5, and 4. And as noted in the paper, this particular order was chosen as it transposes the lowest 2 nibbles of the case index when under a 180-degree rotation in the cell. Aside from case indexes of 0 and 511, the case index is valid and it can be used to look up the equivalence class. Because of the necessity to detect geometric inverses, the high bit of the equivalence class is set to indicate a reverse triangle. To reduce waste and provide reuse, new vertices are only permitted to be created everywhere except along the minimal edges of the full and half resolution faces, and this is the same as saying high and low resolution face. And as can be seen here, these are the 10 locations and their indices for reuse. It's 3, 1, and 4, 0, 6, 2, and 5, and then 8, 7, and 9 on the half resolution face. Also, if you take a look at the second set of images below, you can see why these indices are given as such for the edges. As 83 lines up with 3, 84 lines up with 4, 88 with 8, so on and so forth. For edges, each of the 16 choices is assigned those 8-bit codes, 83, 84, 89. These codes provide the mapping to a preceding cell and the edge from which it may be found in that cell. The high nibble of the code indicates which direction to go, with 1 or 2 determining whether the A or B axis should be traveled, and do note that these are never simultaneously set. The bit values of 4 and 8 indicates a new vertex is created. In the case of 4, this vertex is on an interior edge, which it cannot be reused, and 8 is on a maximal edge, which it can be reused. The low nibble of the 8-bit code gives the reuse index that is used to sample a previously generated cell or write the index of the reused vertex to the current cell. For corner cases, which arise when one of the samples is exactly 0, meaning that the surface passes right through that spot, the vertex is placed at that location. New vertices are still only allowed to be created at locations not lying along the minimal edge, which leaves us with sample locations 4, 5, 7, 8, and C. Meaning any other previously created vertex from a preceding cell is used, can be reused. Like edges, each of the sample locations is assigned an 8-bit code with an analogous meaning. The high bit specifies the reuse direction / permissions. The low nibble specifies the storage slot of the vertex in the cell. Similarly to modified marching cubes, a delta mask is used to determine whether or not a preceding cell exists to be used for reuse. In the case that the bit value 1 or 2 is set in the direction code, but not in the delta mask, a new vertex is allowed to be created for that current cell. 4 and 8 are never valid and are used for interior and maximal edges, to force new vertex creation all the time. One last thing to note is that for edges, points, the calculations must be done with edges having endpoints in the subedge of the cell, and I will explain this in more detail when I go over surface shifting. So now we will begin to look at the code and see the implementation that works with two transition axes. When determining the total number of transition cells to visit, we take the base number of cells per block, and in this case it's 16, and then shift that by the difference of the max world LOD and the current LOD. Since each progressively higher resolution mesh is twice as many cells as the previous, this will give us the correct number of cells that will be extracted for the given LOD. This is a slight departure from the paper, but it's a result of the modification mentioned earlier to make each block cover the same size for each level of detail. Regardless, this change doesn't impact the triangles that are extracted, only how many of them there are. After the number of cells is determined, the history buffer is created with enough storage for 2 rows of history, similar to the modified marching cubes algorithm. We also store the beginning point of the history buffer to quickly reference and reset when we overwrite and switch transition axes. We also now create and set the delta mask for validity checks of reusable vertices to 0. After we've done this, we can begin the extraction process. The first 2 are along the minimal faces of the block, and the next 2 are along the maximal faces of the block. Each time, the X face is extracted first, and then the resulting Y face. In between each change to the face, the storage buffer is cleared back to 0, as well as the delta mask being reset to 0. For any extraction, we loop over the A-axis first, and then the B-axis with respect to the local coordinate system defined by n. Luckily, in both possibilities, B is always the K-axis, so A is whichever axis n isn't, which n is the transition face. So for the X extraction, we go over the J chords for a given K, then increment K. For a Y extraction, we go over the I and then increment K. When extracting a block face, we supply the parameters with one of the predefined indices for at 0, meaning minimum X, up until 3 for the max Y. Similarly to marching cubes, the extraction requires quite a few things: the field parameters, the IJK coordinates, the history buffer, and the delta mask, as well as the relative caches for writing vertex and triangle data to. We also need the current LOD and the block corner for offsetting the I, J, and K element. In addition to these, we also introduce an axis variable that is used to switch on, which specialized helper functions is used in the general extraction method. We also supply a reference to a vector for writing the vertex indices on the half-resolution face. The half-resolution vertices are handled a little differently later on, but the extraction for them is still the same. The vector is used when validating the block. With all this, we can now begin the extraction process. As previously seen, this will be the distance array that's used to store the voxel samples that are loaded. This will be the cell storage, and it is used as the axis to switch on, and depending on which axis, you take the nth element of the A-axis. Once we have the cell storage, we can go through and set each of the reuse values to the flag value, which will be used in a later check. We can reconstruct the base sample by adding in the block corner and shifting the I, J, and K elements by the current level of detail. And once more, by switching on the axis variable, we can load the correct case index given the proper transition axis. After the case index is retrieved, we carry on in the marching cubes fashion of loading the class and the class data from their respective transition tables. Here, the equivalence class is ANDed with 7F to strip off the inverse bit, which is subsequently checked for now, and the geometry counts are retrieved to determine if the cell is valid. If the cell is valid, then the vertex and triangle counts are extracted from the geometry counts, and the vertex code is sampled from the transition vertex data table. Now, for each vertex in the vertex count, we get the vertex corner codes for the given vertex in the vertex code. The corner codes are found by extracting the high and low nibbles of the V code's lower byte. Here we determine if the sample belongs to the half resolution and is done by checking if either sample is a corner of the half resolution side, in which case we determine the entire sample will belong to the half resolution side. After this, the respective distances are determined for the given corner in the samples and the interpolation parameter is calculated. Here we make another switch with the axis variable to determine where the sample positions are based on their respective axes. Also, I would like to mention that these specialized functions I will go over and show, but currently I just want to go through the generalized process of extracting the transition mesh. By checking if the interpolation parameter is not 0, we can determine that neither sample belonged to a corner, in which case that sample will be along an edge. If we determine that the sample does in fact lie along an edge, a check is made whether or not surface shifting should be applied. I will explain this process a bit later, but this is part of what I mentioned earlier about a previous technique that was used to shift vertices on the high resolution mesh, but led to surface morphing. Here, the surface shift is applied to the lower resolution meshes only to avoid the morphing. The paper mentions that surface shifting needs to be done only if the LOD is greater than 1 or if the sample is along a half resolution face. The reasoning for this is that because at LOD 1, the full resolution face is just the regularly sampled cell, so there's nothing to shift. When you get to the low resolution side, suddenly you need to check what you missed in the detail sampling. After the surface shift is applied, should it be needed, we pull out the reuse information from the upper byte of the V-code. Here, we make a check for vertex creation against bits 3 and 4 of the reuse mask. Should it pass, the vertex is created and incremented and position is created using the interpolation parameter. Another check is made against the 4th bit of the reuse mask to determine if this vertex may be reused. If so, the flag value is overwritten using the vertex index at the given reuse code. We then record the vertex index for triangulation and check if the sample was on a half resolution face. If so, the index it belongs to is recorded. Then we simply continue on to the next vertex. If bits 3 or 4 were not set in the reuse mask, then the delta mask is ANDed with the reuse mask, and if the directional bit is present, then the vertex is reused based on its axis, again using the A-axis coordinate. If the delta code failed, then a new vertex is generated similarly as before, and the same check is made as well as the triangulation and index caching. Now, if the sample was at a corner, we follow similar steps but first determine which corner the sample is. Then, using the corner value, we index the transition corner data and the reuse code is extracted from the low nibble. Again, we check against bits 3 and 4. If this passes, we create a new vertex and make the same reuse and caching checks as with edges. Similarly, if bits 3 and 4 were not set, then the delta code is created by ANDing the high nibble of the corner data with the delta mask. If the delta code is valid, the same steps are taken to find reuse. After this, the vertex index checks against the index address, and if one was found, it points to it now. If not, the flag is set in the vertex. Similarly, if the reused vertex was not previously generated, it will also have the flag value and force vertex creation as mentioned in the paper. The same steps are taken to create the vertex, but there is no reuse permitted in this case. Likewise, after this, we cache the information. After each vertex is generated for the cell, we determine triangulation from the class data, and this is used to sample into the class or the cell vertex index cache. We also use the inverse winding variable to determine if the triangle should be given an order of 0, 1, 2 or 2, 1, 0. Full disclosure, I did notice that on the max X face and the min Y face, the triangles were reversed. I'm not 100% sure why this occurs. My main two guesses are either the flipping from XZY to XYZ in world space, or an incorrect axis ordering in extracting the face. With that being said, this hacky check to reverse the current winding does work, and the triangles are all oriented in the correct way. Now, with the generalized algorithm out of the way, we can talk about the specialized functions, and the first two we will look at are loading the transition cell case index. As previously mentioned, ordering in which the bit shift occurs isn't incremental, but follows the bits of their ANDed values, as you can see here. Something else to mention is that even though we only take 9 samples, the 4 corners are duplicated to the half resolution face. So in both cases you can see distance 9 gets set to 0, which gets set to the sample from getVoxel. The same is true for 10 and 2, 11 and 6, and 12 and 8. When loading the samples from getVoxel, you'll still want to follow the regular marching cubes load cell, where you load the main sample, then sample along the A-axis, then go up a row and start over. In this case, you would load the 3 samples on the current row, each time beginning with no A-axis offset, a half-step offset on the A-axis, then a full-step offset. Then you go up the next row, which is a half-step offset along the B-axis, follow the same steps for the 3 samples on the row with the constant half-step B, and then you repeat for the final row with a full step along the B-axis, and then the same manner for the 3 A-axes. This is the generalized process for loading a transition cell, and these are the same A and B axes that are determined by the transition normal n as mentioned in the generalized implementation. The next specialized methods to look at are those for calculating the position offsets for the sample. This is done by referencing what the corner sample is and checking against the transition offset table. Note that this table is not found within the Transvoxel tables, it's one that I created, and I will show a picture of it along as with the rest of the helper structs. The table simply maps the number of half steps taken for a given AB axis to end up at that corner. Then these steps are then applied to the appropriate axes and returned as an integer 3D to offset the base sample. Now this is the big one, surface shifting. This actually plays a role in some changes to the modified marching cubes algorithm we will take a look at later as well. Surface shifting takes advantage of the fact that when triangulating over multiple samples, ultimately the point will only lie in one subedge of the entire edge, where the subedge is the lower and upper edges broken up by the middle sample of the full resolution face. Because the sample can only end up in one of these places, we recursively check which subedge the terrain is passing through, and choose these as the 2 endpoints to create the sample with. This is repeated until the highest resolution, and the process itself is actually relatively straightforward. Given the current endpoints of the edge, add them together and take the midpoint. Then find the voxel sample of this midpoint. Now determine which of the 2 ends of the current edge is inside the terrain. If the lower endpoint is inside the terrain, check if the sample is inside the terrain. If both are in the terrain, then update the endpoint of the edge to be the new sample point. If the sample is outside of the terrain, then shrink the edge down by moving the upper endpoint of the edge down to the new sample. Conversely, if the original point of the edge which passes through the terrain is the upper edge, determine if this sample also passes through the terrain, in which case we shrink the edge in a similar fashion as before, and if the edge should grow upwards, we do it in the same manner as well. After the sample has been determined, repeat the process at the next highest level of detail until ultimately the final results are returned, stored in the reference variables D0 and D1. Finally, I believe reusing the transition vertex is the last function that needs to be shown. Here, we very similarly to modified marching cubes create delta offsets for the A and B axes depending on the bits of the delta code. The B axis determines whether row 0 or 1 should be used, and then the A axis determines where into that row we should find the reused vertex. The reuse code is then used to return the potentially previously generated vertex index code. Before I head off and show a demonstration of the extraction, we need to go over some augmentations to the modified marching cubes algorithm I showed in the previous video. As previously mentioned, the number of cells visited is now determined by shifting the base number of cells per block by the LED offset. Inside of the processing cell, At the beginning, we create a face mask variable and do a check if this block is at a lower than max resolution. If so, we determine where this cell is. Should it be along either of the X or Y faces, a flag is set that the face mask is used later to track shifting information for these triangles. This is different from the surface shifting, and I'll unfortunately have to go over it in part 2 because this is already running much longer than expected. The only other change is at the bottom, where a check is made against a second table, and I will also show this table later. And it's used to determine if a particular face mask value maps to two faces, in which case the vertex is extremal, which requires even more bookkeeping than normal vertices along shared faces. However, if the face mask has a set flag but does not map to a shared face, then we loop over each face and find the face it belongs to. I do suppose you could use a third map to avoid having to do this loop. However, this should be the last change, and if I missed anything, I will try to make sure to mention it in part 2, where I'm going to go over the rest of this supporting code to make the entire thing work for transvoxel meshes, and how to make them actually useful and workable. But in the meantime, I will now show the overall results. Alright, so this is the first demonstration I would like to show, where we have 3 levels of detail going on. We have level of detail 0, level of detail 1, and then level of detail 2 happening in this far corner. Another thing I would like to show is, as the paper mentions, it's kind of hard to see, but here for these two at LOD1, because they're only transitioning on one side, we pick the lower resolution vertex, and they come at a kind of an angle like this in the corner. However, because this mesh is transitioning on both sides, it's very difficult to see, but here at the top, the primary mesh has actually been pushed in on both sides by the transition mesh, which is this little black triangle right here. There is a surface normal issue with the transition meshes. However, I'm not too worried about that right now, as I can focus on that in the next test, which will be shading, and I misspoke last time. I said trilinear interpolation. It is triplanar projection, not trilinear interpolation. But I do plan on making another pass to clean up the surface normals of the transition triangles. As you can see here, they're not particularly pleasant to look at. However, the main key here to look at with the transition triangles is that there is no cracking along these 3 different levels of detail. And this is just a second view I would like to show of when you're only transitioning on one side. So these both are LOD1, so on this shared face they're the same, but these are both LOD0, and it's a little difficult to see, but you can kind of see how the normal transition meshes are right here, and then right here at this shared maximal vertex, they favor not the transition vertex, but the actually primary vertex, which gets rendered. Again, it's a little difficult to see, but it is there. Stay tuned, and next I will be showing Chapter 5, the shading and triplanar projection.